Now it's working. So when you get to your y equals here, I just want you guys to see what's happening. First of all, if your stuff is all sorts of messed up, if your window's all weird and whatnot, do a quick reset. Do a second plus 712, and then do a second plus 722. And that'll just reset defaults and everything. It'll put you back to a 10x10 screen, so you don't have to mess around with it. Your windows go back to normal. Anything that was left in your y equals, if there's something hiding, you don't have to try to figure out where it went. What did I say? 3 to the x, 4 to the x, 5 to the x? Okay, so 3 to the x, 4 to the x. And then graph it. Kind of does, but what's changing? Yes, the rate at which they increase. And that's because of the 8 value, the multiplier there, the lead term. One thing is, you were saying it all kind of looks the same. Don't all three of those have the same y-intercept? Yeah, when you have the y-intercept, that's when x equals 0, right? And if x is 0 for each one of these, what's the y-intercept always going to be? It's 1. Okay? It's always going to be 1. And when x is 1, you're always going to get that value then, right? Same idea. Okay. So what happens is we wind up seeing that when x equals 0 is your y-intercept, and when x equals 1, your y value is the b. That b value is what we call it b to the x. Okay? And that's how this. Fine, we'll call it. All right. So you start to see stuff like that. Did it ever go below 0? No, it did not. So you always had, if it doesn't go below 0 and it approaches it, we call that a horizontal asymptote at y equals 0. Okay. Remember how you draw an asymptote? Just dotted line. Okay. Dotted line. Or if worst case scenario, let's say you're trying to draw it and you know it's at y equals 0. You can just say, point to it and say dotted. Okay. Remember we did that before? Some of you guys use pen, and if you go back and you realize, oh nuts, I forgot to dot that. If you ever just draw a little arrow to it and say that's supposed to be dotted, I'm perfectly fine with that. That works out. That works out well. Okay. As we go through. So again, exponential. These are what we call exponential growth. They're going to move from left to right, up like that. There's a couple other things that happen with them. We're going to call these things a parent graph. And the parent graph is in the form, that's right here, of y equals b to the x. That's what we're calling our parent graph. The stuff that we found, I forgot that. Yeah, right. We found the y-intercept was when x was equal to 0. The x-intercept did not exist because it was an asymptote. The horizontal asymptote is what the curve was approaching, never got to. That was the line at 0. The domain was always all real, because it's moving from left to right. And the range was always above, in this case, it's above our asymptote. Okay? And that's where this stuff works. We call this exponential growth because the value of b is greater than 0, and it's not equal to 1. Because if it was equal to 1, what would it always be? 1. And it wouldn't be exponential, it would be linear. Right? That's where this stuff goes to. Let's see. Exponential growth, exponential decay. The graphing of it's okay. I think these are some of the, when we get to the word count stuff, they actually make more sense. Because like I said, we're talking about money. We're talking about appreciation, depreciation, car values, things like that. So it actually has a little bit more real world application to it. So with every parent function, what do you think comes along with it then? Or a shift? A kid function, correct. So that's what we're going to wind up doing here then next, is that we're going to look at, let me see if I can write this a little bit cleaner. It's a times b to the x minus h plus k. It's your h and k, your horizontal and your vertical. Okay. So what's going to happen here is that the way that we're going to work with these is that you get a value up in front. This a value we treat it as a scalar. What's being raised to the exponent is the b value. Your h is always tacked on to the exponent. A lot of times it'll be grouped in parentheses. Sometimes it is, sometimes it's not. If there is no value, if it's just to the x, it means your h value is 0. The k value is always pushed off to the end where it's like a plus or a minus. That's the up or down shift on things. Like I said, every one of these a, h, and k's, we've all worked with these before. What they do is they transform the parent graphs left and right, up and down, and the scale of it. As we get going into these things, you'll see how relatively easy it is to work with. Right. Excuse me. For example, if we look at, this one's the easy one first. Y equals 1/2 times 3 to the x. Whenever we do this type of stuff, especially with the graphs with parent functions and shifts, you're going to always ask me to say, or hear me say, label your A, B, H, label everything out first. That way you know what you're working with. This becomes, it's pretty easy with the exponential growth decay things, but as we get to trigonometric functions later on with sines, cosines, tangents, and secants and cosecants and all that, they get real messy if you don't know how to differentiate between what values we use. This is good practice to start learning how to do all that. So, as we go through this, what's your value of A? Okay. What's H? 0. And what's K? 0. So is there a shift horizontally or vertically? No. Nope. So basically what we're doing is we're going to plot just the parent graph. The parent graph here is, again, we're just going to use simple values. -2, -1, 0, 1, 2. I always like to fall back to some very easy values to work with to start to show how this stuff is going to look. As it gets more complicated, I'll show you guys a nice trick to help you through some of this. Okay? So if I use -2, that means it's 3 to the -2, which means it's 1/9. So you get 1/2 times 1/9, 1/18. Then the next one you get 1/2 times 1/3. Are we okay with that? 1/6. Now, what's 3 to the 0? 1. What's it at 0 now? 1/2. It's going to be your A value. Okay. And then at 1, it's going to be 3/2. And then 9/2. Are we okay with that? Now, again, it's not that the mathing of figuring out your ordered pairs is going to be tough. More often than not, I'm going to ask that you guys list, like we've done before. I'll just ask you to list your ordered pairs. And when we get to your shifting of these things, you're just going to add to your parent values, your H and the K. And it works really clean. I know graphing some of these weird fraction ones are kind of a pain, and it's not absolutely perfect, set in stone, and that's okay. All right, we're getting the general consensus of what it's going to look like. So we go back with our H value and our K value being at 0. We know that our horizontal asymptote is at 0. It's our K value, so we know that's here. Okay. From there, at -2 was 1/18. Well, I don't know. That's about here-ish, and then here-ish. Then it jumps to 1/2. Then we're at 3/2. Then we're at 9/2, which is what? 4.5? There we go. It's relatively straightforward. That's a really easy way of looking at just the parent graph. Because there's no H and there's no K, I would just call that its parent graph, the A, B to the X. If there was an H and a K, then I would do something with each one of those points. Speaking of H's and K's, guess what we're going to do next? SMRT. Okay.
No.
So let's try this. 3 times 2 to the x minus 1 minus 4. All right. So again, what's your A value? 3. H? 1. Remember, it's x minus h. So what's your h? It's 1. What's k? Negative 4. Okay. Now, what happens here is that your A value, or I'm sorry, your H value is always opposite of what you think. And that doesn't change. The K value, like we saw before, when it's tacked on the end there, it is whatever it is. So, we kind of do the same thing. Pick out our values, and then we're going to move them. Let's see. Let's do this. We have a little bit more space. So my parent function, I'm just going to make a table here. I'm going to do 3 times 2 to the x. Oops, that goes down the wrong side. X, and this 3 times 2 to the x. And again, we'll do negative 2, negative 1, 0, 1, 2. 2 to the negative 2 is a fourth. So it's 3/4. 3/4. 3/2, then what? What's that? We're going to plot the parent function first, and then I'll show you the trick for how to get your shift function. Okay? So what we're doing is we're going to plot the parent, and then shift. By doing it this way, Sarah, it takes away a lot of thinking. It makes it easier. All right. It might take an extra minute, but it's less work on your brain, which I'm sure most of you would be very happy to hear. All right. 2 to the 1 is 2. 2 times 3 is? 2 squared times 3 is? Well. All right. So these are my... Yes, ma'am.
Well, like, if it's a parent graph one, or it's just like e to the exponent times 3.
Because if I put the scalar in now for the parent graph, because originally our basic graph was just b to the x. Well, that was in front of the b was a 1. Does that make sense? So I probably should have said that there's a 1 there. That would have been cleaned that up for why I'm doing it this way. All right. So now if you think of it, there's a scalar to the exponent. That never changes. That curve won't change. What we're doing is just going to move it. Okay. So if I first plot these, we have negative 2 and 3/4. Load this up a little bit here. Oops. Negative 2, 3/4. Negative 1, 3/2. 0 and 3. 1 and 6. 2 and 12. With the parent graph, where's the horizontal asymptote? 0. Well, there's no h and k in the parent. The parent graph is going to have it at 0. All right. So now, when we graph parent graphs, do you guys remember when we dotted them? Do you vaguely remember that before you shifted them? So anytime we plot a parent graph, we dot it. And then from here, we shift it. Our h and k of this one was what? 1 and negative 4. That means for the shift, it's going to be x, it was plus 1, right? Yeah. X plus 1, and then it's going to be y minus 4. So what happens is, for each of these ordered pairs that we started with, was it?
It's positive 1.
No, it's a positive one. Yeah.
Yeah, because it was x minus h in the numerator. Or not numerator, excuse me, it's the exponent. Okay. So, what's nice about doing this is kind of what you're getting at here, Sarah, about why don't we just do the 1s and 4s right away? Because now, what's negative 2 plus 1? What's negative 1 plus 1? See what I'm saying? I know that this one's going to be negative 1, 0, 1, 2, and 3. What's 12 minus 4? 8. 2, negative 1. And then we have a couple of fractions to worry about. But notice, the denominators aren't terrible. Okay? 3 halves and subtract 4, so that would be what? 8 over 2, so it'd be negative 5 halves. Does that sound right?
Yep.
And then 3/4 subtract 4 would be negative 3 1/4. Is it okay if you do mix in a couple of mixed numbers, as much as I loathe them? In this case, when you're just taking 3/4 out of 4, could you write negative 3 1/4 without doing a top-heavy fraction? And that's okay, all right? There's a time and a place for mixed numbers, and every once in a while when you're looking at ordered pairs, because you're going to be plotting close-ish anyway, it's okay, all right? Now, your original horizontal asymptote is at 0. Where does it have to move to? Which way is it moving? Is the horizontal asymptote going to move up or down with this, you think? It's going to move down, so it's got to move down how many spots, though? 4. So your new asymptote, your horizontal asymptote, is going to be at y equals negative 4. Your horizontal asymptote will always be at your k value for whenever you graph your parent. So if your points go past that and all that, you know you're screwing something up. All right. You know what is it? You know you don't do.
Yeah.
All right. So I put my asymptote in. I'm at now negative 1, negative 3 1/4 here-ish. 0, 5 halves is what, 2 1/2? Negative 1 and 1. 2 and 2. 3 and 8. And here's my shifted function. Parent and shift. It's very systematic. Do this, do this, do this. Okay? And once we get the procedural part done, graphing of these things is really easy. It's really easy. All right? Now remember, right now we have growth is for when our b value is greater than 0, and then it is but not equal to 1. Our decay then is going to look a little different. Oh, I'm sorry. Can I have an a value that's negative? Yeah. The only difference with that one, do you have your calculators out still? Do me a favor, go back to your calculator real quick. Were you guys okay that these were exponential growth values, correct? Because your b value was greater than 0. So real fast, just go to your y equals, back out the 4, and the 5, and just do a negative 3 to the x. Yeah. It just reverts it. Okay. It's still technically a growth because the a value is just negative. All right. Does that make sense? All right. It does. Okay. So let's look at decay then.
Why did you make me ask
Well, they're curves, so they're not.
That's why it's a joke. He asked the question. It's about your student.
Okay, so again, we just did this. Growth, decay is going to be between 0 and 1. Notice it's not negative. And notice it's not equal to 0. Excuse me. Oh, it's ever bigger than 0? I'm bigger than 1, but it's not equal to 1. Wow. Good morning. Hi. You and me both there, sister. Okay, so the decay value, remember, we're not going to get a decay value that's going to be less than 0. Because if it becomes less than 0, that means the A value is what's negative. All right? So your B values that are fractional between 0 and 1 show decay. And we'll do another one here real quick that's an easy example of what that looks like. Instead of going up like this, it's just going to go the other direction. It's going to go down like that. All right? It's really simple as we get into some way they look. As you do a few of these, you'll start to pick out the differences in between the two. Let's do this one, but I'm going to put an H and a K into it. So we'll do maybe a minus, I'll do a plus this time. We'll do a plus 1. We'll make it like that. So we have an A, H, and a K. Maybe we should probably start putting in here, what is our B value as well? 5. Nope. So what I'm doing here is I'm adding the x plus 1, so we have an h value in here, just so we can work with another h and the k. So we have an a, b, h, and k to look at. Our a value is 5. Our b value is the 1/2. Since that's 1/2 and it's between 0 and 1, that makes this decay. All right? So we know this is decay. That's a really good question that you'll see on tests sometime, real quick, and just ask you, is this growth or decay? There's your answer. If it's between 0 and 1, decay. If it's greater than 1, growth. Does not matter if the A value is positive or negative. Right. Our H value here will be -1, our K value is +2, which means when we're all said and done, where will your horizontal asymptote be located? It's got to be at 2. So again, we pick out some ordered pairs, and I'll flip the screen here so we can do this. So we will have 5. All right. What's 1/2 to the -2? 4. And what's 4 times 5? 1/2 to the -1 is 2. 2 times 5 is 1/2 to the 0 times 5. 1/2 to the 1. So you have 5 halves, and then 5 fourths. Are we okay with me on that?
Yes.
All right. Now, with the H's and the K's, we go ahead and start our next set of ordered pairs. Oh, here, let's plot this first. Sorry. -2. Let me just move this all the way up here. Bring this to the front. All right. At -2, it's 20, so it's up here. Okay. At -1, it's 10. 0, 5. 5 halves is 2 1/2. 5 fourths is 1 1/4. And remember, it's going to move and approach 0. So it's moving down. Down and right is decay. All right. To each of these ordered pairs, our shift, I forgot, it was. I knew it was x. So it's -1 and +2. Okay, thank you. Right. So your h value would be -1. So you're going to subtract 1. That the h is. Oh, I'm sorry. Yeah. And then the other one was y +2. All right. So this is our shift from your h and k. Our h was -1, our k was +2. And again, you'll notice, once you plot those first values and you substitute them in, the mathing of it is really easy. Now you know how to work with exponents and flip fractions and all that kind of stuff. That's where we get into this stuff. That's why we do that chapter we just did to be able to do this. So now we go through and just adjust it. So it's -3, 22. -2, 12. -1, 7. And then, what was this? 0. 5 halves plus that is what? 9 halves? And then 1 and 13 fourths. Okay. And once again, what stinks is that we know that our new horizontal asymptote will be at y equals 2. So we plot that first. Unfortunately, with the 10 by 10 graph, I just say it's up here. And the next one's, I can kind of get to it, maybe, ish. So -2, we'll say it's about here. Should probably change color. And then -1, 7, 0, 9 halves is 4.5. And 13 fourths was what? 3 1/4. And we know we're approaching it. And there you go. What's your domain? All real numbers. What's your range?
Y is
Everything greater than 2. Yes, ma'am. Oh, this is your horizontal asymptote, your new horizontal asymptote. And it's always your K value. All right, your K value is always, whenever you're done shifting everything, your K value will always be your horizontal asymptote. When you do your parent, it's always at 0 because there's no K value.
It's always at 0?
Yep. Because there's no K value at your parent function. So remember your parent, it's going to be at y equals a b to the x, and your shift. You go from there. Not terrible, is it? Honestly, the worst case scenario is sometimes you get big numbers that just don't plot. They're not really friendly plottable. So what I normally do with this stuff is that when we do quizzes and all that, I tend to make sure that they're plottable within a 10 by 10. What? You could sit over here. So you wind up with, I try to make sure that they're plottable. If not with a 10 by 10, I don't think I'm using anything than that. I think I might have 15 on one of them. I have to go back and look at some of my stuff, but it's usually fairly plottable. With exponential growth and decay, I know how much I don't, you guys probably notice I don't use a ton of graph paper. This is one that works pretty decently with graph paper. It helps keep it a little bit cleaner as you're plotting them through. That's just my own opinion on this one. When we get to other graphs later on, trig functions, we won't use graph paper for that. So it's really not needed big trig function stuff. I think that's really all I had. Questions at all? It's pretty straightforward. Give this stuff a shot. They're over the 2 sections. I believe. Oops, wrong button. I think. We double check here. 1, 2, 3. 1, 2, 3. Plot the parent in the shift. List ordered pairs. List your ordered pairs. Do the domain and range, just like we were doing here. Okay. There's 6 of them. All right. So we'll go through that. Tomorrow we'll look at graphing E as an exponential. There's a rule for what it came from. I'll show you that real quick. And we'll go from there. Tons of fun. I'll be right there. What's up, lady?
So I did this one
It's between 0
I do too.
What happens with all of these, domain is going to be called. Domain is one possible value of x. Any value of x is right here, you're going to get a value of 1. So your domain is all real numbers. Your range, if you look at it, this graph is below the line above 0. So it's the range is below 0.
It's not going to be like anything else.
So the range, I know the range is like, it has to be greater than 1 for possible values of y.
It can be greater than y, it can be less than y, depends on the direction of the graph.
So yeah, so if it's like 2, it's also not greater.
It depends on what if the value is negative or positive, it's flipped over. Don't fall into that. Where does the graph go? Above it or below?
And then the domain is like,
All real numbers. Guys, remember, exponential functions, there is no restriction upon the real numbers for x. Exponential functions are always all real numbers. There's no restriction. We'll get into restrictions when we get to logarithmic functions, and that'll be not next week. It'll be the week after. No, logs, they're big, they're heavy, they're wood. Bad, they're good. You know the reference? I thought you were because you I thought that was something you would have gotten the reference of. You got it? I just somebody always gets a little bit of it.
I did. I was so confused. I go to the bathroom.
What was you?
I couldn't find it first.
I think that time on that mascara.
Yeah, no.